Hi, ch12. So I didn't get any questions from last day's questions. Um, Make sure, again, if there's anything you're not understanding, that you let me know and I can go over that. Um, so today we'll look at acid-base titrations. Um, so the reaction that's involved is a neutralization. So here's, this is definitely one of the labs we would have done. Um, so this is a titration setup. So the point of a titration is so that you are able to determine an unknown concentration. Okay, so let's look at the components here. Okay, so this is a burette. Okay, so a burette is something that's got a is used in analytical procedures. It's all marked with volume. At the bottom, you have a valve, which basically controls how much flow you're going to get coming out of the burette. So if it's opened all the way, it'll drain out really fast, and then if it's partially open, it'll go dropwise. And so we call the solution in here a titrant. It has known concentration. The other word for the one that has known concentration is we refer to that as the standard. Okay, so that's the standard. And then you've got a clamp here, a burette clamp. You can actually put two burettes, so you can have another one ready on the other side. And then here's your ring stand. And inside this Erlenmeyer flask is the analyte. So this is what we don't know the concentration of. Okay, we're trying to determine. The reason why you want to use the Erlenmeyer flask is because it has a narrow opening at the top, and that way the contents coming into the flask won't splash out. Okay, as opposed to, like, say, using a regular beaker. So here, again, this is a standard that has known concentration. This one has unknown concentration, but it has a known volume. Okay, so we know how much volume we put in there, and then we add in some drops of indicator, 2 or 3 drops of indicator. So an indicator is a chemical that will change color in different pHs. And so what happens is you use the appropriate indicator for the titration that you're doing. And so what you're looking for is, within a half drop of the standard coming in, it should have a permanent color change. And at that point, you've reached what we call the equivalence point or the end point. Now, with the burette, you'll have some initial reading here. So let's say that this is like 15 milliliters, and then it'll drain out until you get to the end point by monitoring the color, and then you look at whatever the reading is here. So let's say this is 45 milliliters. Then you say, okay, well, we used 30 milliliters. So what you're trying to determine is how much of the standard is required, what volume is required, so that I get to the end point. And the end point, again, is where you've achieved neutralization. Okay, so again, the moles of the standard equal the moles of the analyte. Okay, so we refer to that as the equivalence point. So let's look at some questions having to do with this. Okay, so the first one here, so we're going to use the titration to calculate unknown concentration, and this is typically what you would be using it for. So the one that's the standard is the one that you know is the concentration. So this is an acid-base titration. So either the acid or the base is going to be the standard. So in this case, it's the base because we know the concentration. Okay, so this would be your standard. Okay, so there's your standard. So this would be in the burette. And then here's your unknown concentration. We don't know what the concentration of H2C2O4 is, but we have the measured volume. Okay, so this would be what's in your flask. Okay, so you'd have 50 mils of this in the flask, and then plus some drops of indicator. And what you would find out is that you need to empty out 38.75 mils from the burette into the flask so that you get a permanent color change. So that's why we know that this is the amount required for neutralization. Now, typically what you would do is you would do several trials and then you would take an average. And when you take the average, you discount any values that are kind of off by quite a bit. So you only take the average from the values that are pretty close in relation to one another. So here's our reaction. And so it's important that you have this balance. Okay, so again, this is a typical neutralization reaction: acid, base, water, salt. Okay, and then we balance it. This type of acid, remember, is called a diprotic because you have two hydrogens. Okay, so here's the concentration, here's the volume, so we can get the moles, and we'll use millimoles here. Okay, so milliliters, and then there's your concentration, and there's your millimoles, and that's the NaOH. And then from the NaOH, we want to go to the H2C2O4, and because that's a 1:2 ratio, we multiply that by a half. Okay, so now we have the millimoles of the H2C2O4, and then you can get the concentration. Okay, so you divide it by 50 milliliters, and so millimoles is good because you don't have to convert your volume to liters then. Okay, it cancels out at the end. Okay, so again, this is an analytical procedure to determine unknown concentration. Now, beyond that, you can do other things as well. You can calculate percent purity. Okay, so in order to calculate percent purity, what you're going to want to do is take your basically take your calculated or actual. Yeah, actually, let's use actual. Your actual concentration and divide it by your theoretical. Okay, so you take your actual concentration that you are able to figure out experimentally, you divide that by the theoretical, which is what you would calculate it should be, and then you multiply that by 100%. Okay, so that'll give you the percent purity. So here's some sample of NaHSO4, and this is impure, right? So we want to basically figure out how pure is it, and then it's diluted to 250 mils. So you basically make a 250 ml solution of that, just dissolve that in water, and then of that you take out 25 mils, and that sample is what you're going to titrate against. Again, your standard here is NaOH. Okay, so same type of reaction. This one here is going to be 1:1. Okay, so when you're looking at the reaction, basically what you're trying to figure out is mole ratio. That's the most useful thing that you're trying to figure out. So there's the millimoles of the NaOH. Okay, so again, this would be this is the standard. This would be in the burette. Okay, and then that's how many millimoles that is, and that's going to be how many millimoles the NaHSO4 is. Okay, so now we've got the millimoles here, and this was taken from a 25 ml sample, so we know how many millimoles there are in the 25 ml sample, so we can get the concentration. So again, this is the actual, or what you would get experimentally. Okay, so again, you can cancel out the millis, you got moles per liter, 0.1068. And so now what we want to do is so that's the actual, and we want to divide that by the theoretical. So the theoretical, we're going to figure out by getting the moles of this. So take that mass, divide it by the molar mass of NaHSO4, and then divide that by the volume to get the theoretical concentration. Okay, and then we'll divide that from here. So it's going to be this mass divided by the molar mass, and then divided by the volume, and so that gives you this concentration. And so these are the two concentrations you want to divide, and so your percent purity is going to be 92.2%. Okay, and the last one here. So this one, they talk about using molar mass determination. Okay, so a monoprotic acid. Okay, so the significance of the question telling you it's monoprotic, and you're working with KOH, is that you can see it would be 1-to-1. Okay, so monoprotic would be like this one here, the HSO4. Okay, as opposed to diprotic like the H2C2O4. So same idea. Your KOH in this case is the standard. A standard doesn't always have to be a base. I know in these examples it is, but you could have an acid as your standard. So same thing. We want to get the moles of that, and then this is typical. Like you can, when you're talking about an unknown acid, when they call it a monoprotic, you can just refer to it as HA. Okay, to represent the acid. You don't know what this acid is, but that's a way you can represent that. So now we can find the concentration. So same like we did in the previous one. So now we've got the concentration of moles per liter of this here, and this was taken from the 250 milliliters. So we can multiply these two, change that to liters, multiply these two to get moles. And then what we do is we take, remember what molar mass is grams per mole, then you take the mass there and you divide it by the moles. Okay, so that's going to be the mass divided by the moles, and so that gives you 158.1 grams per mole. Okay, so I'll stop there. I'll get you to do these questions out of the textbook. I have those done for Friday, and then I'll go over any of the questions that you have. Okay, so make sure, like we've been spending this class and the previous one a lot of time on calculation type questions. So definitely check your answers in the back of the book to make sure you're getting them. But if you're not getting them, please let me know, and I'll begin my next lesson by going over questions that you have. Okay, so again, be safe and take care of yourselves, and I'll talk to you soon. Bye now.